A metal disc is swinging freely between the poles of an electromagnet. So imagine this disc is swinging freely. So first part, they told you when the electromagnet is switched on. So actually these are not permanent magnets, these are electromagnets. That means when you switch on the current, it becomes a magnet. So the disc comes to rest after a few oscillations. That means after oscillating a few times, that means it will slow down and then finally stop. So state Faraday's law of EM induction and use the law to explain why an EMF is induced in the disc. So you will need to state the whole Faraday's law. So that's why I did. The magnitude of the induced EMF is proportional to the rate of flux cutting. Now you may use rate of change of flux linkage. Also can, no problem, right? So it's either one. But how do we use the law to explain why an EMF is induced in a disc? Because the disc moves, right? So we can talk about cutting of flux. So the second part, as the disc oscillates, it cuts the magnetic flux, so an EMF is induced. Next one, explain why eddy currents are induced in the metal disc. Now, I want you to realize, right, whenever they want you to explain why there is current flowing in anything due to the induced EMF, you need to be able to tell them there's a net EMF. So what is net EMF? I will show you in a short while, right? But let me just tell you something about what is happening. Now, when the disc comes towards the poles of the electromagnet, you'll notice that the front part will be cutting first, all right? But the back portion hasn't reached yet, so the back portion will not cut first, all right? So this will cut. There's EMF here, there's no EMF here, so then current will flow. Then later on, when it passes the pole, the back portion of the disc will still be cutting, but the front portion won't be cutting. So there will be EMF induced here, but not here. So there's a net EMF. So the net EMF means there's a difference in EMF between the different parts in the conductor itself. Then current will flow. So that's what you need to tell them. As the disc approaches or leaves the poles of the electromagnet, there is a difference in the rate of flux cutting. Therefore, there will be a net EMF in the disc and eddy currents will flow. And then the last part, use energy principles to explain why the disc comes to rest after a few oscillations. Now, when you talk about these eddy currents, it is quite easy to explain in terms of the energy that you will lose as heat. So some people ask me, right, can I use like Lenz's law to explain why it comes to rest by talking about, you know, the current flowing here will produce a magnetic pole to oppose the pole when it comes in. So that would be too complicated because they did not tell you which is north, which is south and stuff like that. So what I would say then, you could explain in terms of like, you know, when this one enters, there'll be a current passing through here, then there'll be a magnetic force opposing it, so therefore it will slow down. Again, that will be quite complicated. The simplest way of explaining is just using conservation of energy. So Lenz's law is actually a statement of conservation of energy, so we can do that. So we talk about the eddy currents here. The eddy currents will dissipate energy as heat in the disc. So less CAIE will be available for oscillations and the amplitude will fall. Now what it means here is when it's moving, the disc is moving, it has kinetic energy. Due to the cutting of flux, this CAIE becomes electrical. Then the electrical energy is in the form of eddy current, and the eddy current dissipates energy as heat. So the CAIE drops. That's why it slows down and finally stops. An ideal iron cord transformer is shown here. And this graph, they told you, gives you the current in the primary coil against time t, and they told you that initially there's no current in the secondary coil. So first part, complete figure 6.3 to show the variation at time t of the flux in the core. Now they want you to show them how the flux in the core varies with time. Now I want you to recall the soft iron core is magnetized by the magnetic field coming from the solenoid. In other words, because there's a magnetic field due to this solenoid, it magnetizes the core. So the core's magnetic field actually comes from here. So basically, instead of saying the flux in the core, the flux in the coil is identical, all right, because it comes, the flux in the core comes from the coil. But how will the flux in your coil vary if they gave you the current in the coil? Now you still remember the formula for the flux density of a solenoid, which this is a solenoid, is B equals to mu Ni, where your mu is a permeability, N will be your number of turns per unit length, and I will be the current. So here I wouldn't call it permeability of free space, because this is not vacuum or air, this is a core. So this will actually be the permeability of the core, but it doesn't matter here. The main point I'm trying to say is, since the mu, which is the permeability of the core, and number of turns per unit length are both constant, that means your B will be proportional to your current. So by the way, this is the magnetic flux density. What we actually want is the flux. So how is the flux related to the flux density? Very simple. From the formula, flux equals to BA. The A is constant, so the flux is proportional to the flux density. So from now onwards, I want you to remember this. For a solenoid, the flux in your solenoid is proportional to the flux density is proportional to the current in solenoid. These three will always be proportional, so they will have the same shape. So therefore, the flux in the core, which is what they want, which is actually the flux in the coil, will actually be directly proportional as well. So you just follow back the same graph. All right, the amplitude of course can be different, doesn't matter, but the shape must be the same. That means if you start from 0, you start from 0. If one period is up to here, one period is also up to here. Okay, next part. Draw the variation with time t of the induced EMF in the secondary coil. So what about the secondary coil here? How will you draw its induced EMF? So remember the combination of Faraday and Lenz's law, which is this. So I mentioned to you that the value of the induced EMF will be equals to the negative of the gradient of the flux versus time graph, because you can take out the n here. So the gradient of the flux versus time graph, put the negative, becomes the value of the induced EMF. So since this is my flux versus time graph, do you notice that this is a sine function, a positive sine function, not a negative sine, not a positive cos, not negative cos, this positive sine function. So d and phi dt means differentiating this function. So if you differentiate sine, you're going to get cos, alright? But then you need to put a negative in front, so the value of the induced EMF. So therefore, my induced EMF graph here is actually a negative cos graph. But you must have the same period. So if the period for this original graph was up to here, the period also for the induced EMF is the same. But it's a negative cos function. And then the last part, hence state the phase difference between the current in the primary, which is this, and the induced EMF. So you will notice that they are not in phase. So how do we calculate the phase difference? Can you see, if you take this as a starting, this will also be the starting. That means this starting point is the same as this. So can you see it's lagging behind by a quarter of a cycle? So quarter of a cycle is 90 degrees or pi over 2 radians. You can write either one. So is this standard? Yes. In a transformer, this is what you can expect. The phase difference is always 90 degrees or pi over 2 radians between the primary EMF and the secondary EMF. Next, we are asked to outline an experiment to verify Lenz's law in your given all these apparatus. But you will notice what I did was, I did use the coil, I did use the bar magnet and the ammeter, but I added a variable resistor here as a precaution, because I don't want suddenly, if the current is too large, then you will cause the deflection in the milliammeter to exceed the scale and damage the ammeter or the milliammeter. So this one is optional, but I would always recommend you to put this in, because sometimes you may get extra marks for this. So copy this diagram in your answer, and this is how you will explain, because you just asked to verify only. So you just have to say, when the bar magnet is pushed into the coil, the milliammeter will show a deflection in one direction. When the bar magnet is pulled out from the coil, the milliammeter will be deflected in the opposite direction. Now that's all you need to say. There's no need to explain, because they didn't ask you to explain. They just asked you to outline the experiment to verify. Now the next part, I'm not going to do the whole question, because these are typical questions that we've done before, but what I want to do is spend some time to explain this part. Now remember, in the previous two questions, right, that we did, we said that the induced EMF and the primary current, or even the primary EMF, and the primary current and primary EMF here will be in phase, because the voltage and the current will be in phase here. But the induced EMF here will always be 90 degrees out of phase with this. Right? That is standard. So here they want you to use Lenz's law to explain why the input PD and the output EMF are not in phase. So how do we use Lenz's law here? So remember, Lenz's law talks about the direction of the induced EMF or direction of the induced current always acts in a way to oppose the flux change that causes it. So I want you to imagine that the current in your primary will be in phase with the flux in the primary, because the current will generate the flux. However, the induced EMF here would produce another current, the induced current, that would in turn produce a flux to oppose the flux change here. That means, right, the flux in your secondary coil is not changing in the exact same way as the flux in the primary coil, because the flux here must change in such a way to oppose the flux change here. Alright, and because the flux here will not be identical to the flux here, in fact this would oppose the flux change here, therefore the current and the EMF that causes this flux obviously will not be in phase with the current in a primary coil. So that's the understanding. But how you write it down, you would say this: the induced current in the secondary coil produces a magnetic field that opposes the changing field produced in the primary coil. Alright, therefore the output EMF will not be in phase with the input PD. And for this question, which is similar to the previous question we did, again I'm going to skip the A and the B part 1. I'm going to concentrate on B part 2, because you know what, even though this part is similar to the question we just did, but here they want you to explain why the input PD and the output EMF are not in phase but using Faraday's law, not Lenz's law. So how do I use Faraday's law to explain that? If you remember Faraday's law says that the magnitude of the induced EMF is proportional to the rate of change of flux here. So what it basically tells you is whatever EMF I produce here is not following the flux here. Because you see, it starts from the beginning, the EMF here will be in phase with the flux here. But the induced EMF here is not proportional to the flux here. The induced EMF is proportional to the rate of change of flux here. That means how it changes, not following the flux, but following how it changes. Therefore, they are not in phase. So this is how you explain the magnetic flux in the primary coil is in phase with the EMF in the primary coil. The induced EMF across the secondary coil is proportional to the rate of change of flux linkage. So the EMF of the supply will not be in phase with the PD across the secondary. Now all these M1 are your marking scheme codes, and A0 also are your marking scheme codes. So you don't have to copy that now.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.